So this tutorial is meant to address some main issues regarding to dimensional analysis and sort of to point to the value and the general utility of using dimensional analysis as a problem-solving strategy in chemistry problems. As I'm sure you'll recall from last year's chemistry class that you all took, a lot of what uh, is involved in solving chemistry problems is a lot of multiplication and division, a lot of proportional relationships. Some of those relationships are inverse proportions, some of them are direct proportions, and that influences whether you multiply or divide in a problem. And sometimes it can be a little bit difficult to keep track of what proportions happen to be direct proportions and what proportions happen to be inverse, and whether or not you should multiply or divide to progress from one step of a problem to another. And that to me is the beauty of dimensional analysis, because it takes a lot of the guesswork out of understanding how to mathematically conceive of a solution to a problem. So as an example, let's take a look at this problem that's on the screen right now. Suppose I wanted to know how many seconds there are in 47.2 years. Now, again, I can tell you from my own experience, I don't know of a conversion factor or a comparison between the units of seconds and years that will allow me to solve this problem in one step. And so the strategy I normally take for these types of problems is to just work through the units using dimensional analysis to get to the final solution. And what I mean by that is this. Whenever I set up a dimensional analysis problem, the first thing I do is I write out the given information that's provided in the problem that I'm going to use as a starting point to solve the problem. And in this particular case, it would be 47.2 years. Now, I do know, if I consider the time unit of years, that in 1 year, there are 365 days. Now, the way that it works with dimensional analysis is as you progress from the given through the ratios that represent conversion of units, otherwise known as conversion factors, the important thing to keep in mind is you want the unit in the numerator of the current term that you're working with. You want those units to match the units of the denominator in the next term in a dimensional analysis setup. So for example, here I'm starting with 47.2 years. So that means that I need the unit year in the denominator of the next term so that the year units are diagonal to each other. And if I keep this in mind, it helps me to progress from one conversion factor to the next until I have the problem solved. So picking up from where we left off, now I need to convert from units of days to, say, hours. Okay, well, as it turns out, I know that in 1 day, there are 24 hours. Okay, well, we're still not done yet, because basically we still have to get to seconds. I do know that in 1 hour, there are 60 minutes. Going on from there, I also happen to know that in 1 minute, there are 60 seconds. So let me check my units going on from there and have a look and see where I am. If I take a look, my minute units cancel out. In other words, they're in the numerator of one term but the denominator of a second term. So mathematically, that would mean they cancel out because they're dividing out against each other. The same thing for the units of hours, days, and years. And if you notice, the only unit that does not cancel is seconds. So that means that if I were to stop right now and do the math that's shown to me in this unit analysis or this dimensional analysis, then my answer should be in units of seconds, which is exactly what I'm looking for. Now, the way that this dimensional analysis array works, more or less, is essentially you multiply across the top, and then you divide by each number in the denominators. Now, in this case, the divisions are trivial because basically every denominator happens to be 1 in this setup. But as you'll see in other problems that we work throughout the year, oftentimes those numbers in the denominators are not 1, And so essentially then we would have to divide by those numbers. But in this particular case, what the unit analysis is telling me to do is to take 47.2, multiply by 365, multiply by 24, multiply by 60, and then multiply by 60 again. And if I do that, the math works out that I get 1.49 times 10 to the 9th seconds. Now, you could, in theory, work this out in a series of proportions, but basically, if you take a look at the different conversions that we did, you'd be employing, at the very least, 4 separate proportion steps. And in every proportion problem that you set up, you always have to cross multiply to solve for the variable, and that can get a little unwieldy. And so here, the other advantage to using dimensional analysis is it allows you to quickly, within one line of work, understand where your direct and inverse proportional relationships are so that you can quickly decide whether to multiply and divide. I should also tell you that in terms of the AP chemistry exam, it really is the preferred technique in terms of having work reviewed. It makes it very clear and very simple for the grader to see exactly what math you're doing and how it is that you decided that that was the math that you needed to do to solve the problem. The other thing to keep in mind is a lot of times it's very easy in the field of chemistry to sort of forget a formula that you might need to solve a problem. Like, for example, I can tell you for myself, I often struggle to remember the formulas for converting between the Fahrenheit scale and the Celsius scale. But the good news is if you have a strong foundation in dimensional analysis, you don't even really need to bother with memorizing these formulas. Let me give you an example of how dimensional analysis can sort of help you to figure out a problem, even if you happen to have forgotten or don't know the formula to solve it. Suppose that I want to convert physiological temperature for human beings, which would be 98.6 degrees Fahrenheit. I want to know what that is in Celsius. Now, what a lot of people would do would be to go and check these formulas and then immediately just pick out the formula to get degrees Celsius, which in this case would be this formula right here, and just plug in and finish. All right. Unfortunately, on the AP exam, the formulas for temperature shown here are not included in the data packet. And so if for whatever reason a conversion like this would come up, you would not have the luxury of being able to just look up the formula and plug in and be done quickly. You'd have to sort of, figure it out if you don't have the formula memorized. And so let's think about how we would solve this problem. Now, the way that it works, all right, is we have to consider the temperature scales carefully. We have to consider the Fahrenheit scale and the Celsius scale. These temperature scales are based on the behavior of water. All right, so for example, I'm going to write TB up here. That's the boiling point or the boiling temperature of water. And I'm going to write TF down here. Now, if we think of the Fahrenheit scale, the temperature at which water freezes is 32 degrees Fahrenheit. The temperature at which water boils is 212 degrees Fahrenheit. And so if I calculate the range between these two temperatures, that would be 180 degrees separation between the freezing point and the boiling point of water on the Fahrenheit scale. Now for the Celsius scale, if I were to consider the freezing point of water, that would be 0 degrees Celsius. And if I were to consider the boiling point of water, that would be 100 degrees Celsius. And here, calculating the range is even easier. Basically, the range between these two temperatures would be 100 degrees. And so whenever we do a conversion between the Fahrenheit and the Celsius scales, we have to actually do two conversions. We have to correct for the different ranges between the boiling point and the freezing point of water, and we also have to take into account the different starting points, if you will, on each temperature scale. In other words, the Celsius scale actually starts 32 degrees lower than the Fahrenheit scale. And so that means we have to either add or subtract 32 to correct for the starting point, and we're going to have to find some ratio to correct for the different ranges that encompass the boiling point and the freezing point of water between the two temperature scales. And that's going to involve either multiplication or division or multiplication of these two factors, namely 100 and 180. So going back to the problem, all right, let's have a look. I'm starting with 98.6 degrees Fahrenheit. Now, I'm going to have to decide, should I correct for the different starting point first, or should I correct for the different range? Well, if I were to go and try and correct for the range, then basically what would happen is I would have to divide by 180 degrees Fahrenheit, multiply by 100 degrees Celsius so that my Fahrenheit units would cancel. Right? But if you notice, what's going to happen is I'm going to end up with some answer in degrees Celsius. All right? And this plus or minus 32 degrees would be in units of degrees Fahrenheit. And so I would be in a position where I'd have to subtract some number in units of degrees Celsius by some unit or some number with the unit of degrees Fahrenheit. And so that's not going to work. And so the best thing that I would be able to do that would allow the units to work out is to go and actually do the correction for the starting point first. So I'm going to take 98.6 degrees Fahrenheit and I'm going to subtract 32 degrees Fahrenheit from it. Now, I'm not going to actually calculate that difference right now. As it turns out, I don't have to. If I'm using a scientific calculator to work this out, it doesn't matter. I can just allow the number to display on the screen and then go on with the rest of my math. Now, what I'm going to do then is go ahead and implement the ratio correction. For every 180 degrees Fahrenheit, then I have 100 degrees Celsius. If you notice, this difference will be in units of degrees Fahrenheit, which will cancel with the degrees Fahrenheit from the 180 degrees Fahrenheit to 100 degrees Celsius ratio in this conversion factor. That leaves me with an answer that is plainly and solely in degrees Celsius. And if I do the math, then this would actually be 37 degrees Celsius, which is the correct temperature. Now, I want to call your attention to the fact that basically if I go and reduce this ratio down, both numerator and denominator have a common factor of 20, which means that I can reduce this ratio to 5/9. If I go back to the formula, you'll see that if I want to convert from degrees Fahrenheit to degrees Celsius, then basically I need to subtract by 32 first. Now we know where that comes from, and multiply by this ratio of 5/9. And based on our discussion and the analysis of units, then you can see exactly how that formula actually is derived. So again, this is just to show you and to remind you that unit analysis can be very helpful. It is a way of getting yourself unstuck sometimes when you don't remember a formula or if you're a little unsure of what to do at any given moment. I highly encourage you to get used to this technique if you're not already. We'll be doing some exercises in class, all right, just to make sure that everybody's up to speed with this technique. And of course, if there are any questions, then by all means do let me know in class or shoot me an email, all right? And I will see you guys in class tomorrow.